हेलो बच्चों, इस एपिसोड विच तुसी इन्हां बारे सिखोगे एडजॉइंट ऑफ मैट्रिसेस, इनवर्टिबल मैट्रिसेस ਅਤੇ ਇਨਵਰਸ ਆਫ ਮੈਟ੍ਰਿਸਿਸ। ਤੁਸੀਂ ਇਹਨਾਂ ਬਾਰੇ ਤਾਂ ਜਾਣਦੇ ਹੀ ਹੋਵੋਗੇ। ਡਿਟਰਮੀਨੈਂਟਸ, ਇਵੈਲੂਏਸ਼ਨ ਆਫ ਡਿਟਰਮੀਨੈਂਟਸ ਆਫ ਫਰਸਟ ਐਂਡ ਸੈਕੰਡ ਆਰਡਰ ਸਕੁਆਇਰ ਮੈਟ੍ਰਿਸਿਸ, ਇਵੈਲੂਏਸ਼ਨ ਆਫ ਡਿਟਰਮੀਨੈਂਟਸ ਆਫ ਥਰਡ ਆਰਡਰ ਸਕੁਆਇਰ ਮੈਟ੍ਰਿਸਿਸ, properties of determinants, product of determinants and area of triangles ਅਤੇ minors and cofactors। आओ ਹੁਣ शुरू करिए। First of all, we will see what a matrix is. Matrix. A matrix is a rectangular array or arrangement of numbers enclosed between brackets. For example, A is a matrix whose first row elements are 1, 2, second row elements are 3, 4 and third row elements are 5, 6. Another matrix B is a matrix whose first row elements are iota and 2 iota. Second row elements are -3 iota plus 1 and 6 iota. Here A is an arrangement of numbers 1, 2, 3, 4, 5 and 6 in 3 rows and 2 columns. Matrix B is an arrangement of numbers iota, 2 iota, -3 iota plus 1 and 6 iota in 2 rows and 2 columns. So we can say that order of matrix A is 3 by 2 and order of matrix B is 2 by 2. Also, plural of matrix is called matrices. The elements of these matrices are real numbers, complex numbers or functions, variables, x. The horizontal lines of elements are called rows and the vertical lines are called columns. Now we will see what a determinant is and evaluation of determinant of first, second and third order square matrices. Determinant. Determinant is a function which maps each square matrix to a real or a complex number. It should be noted that only square matrices have determinants. Suppose A be a square matrix of order 1 containing element A, then determinant of A is defined to be equal to A, and if A is a square matrix of order 2 containing elements A11, A12, A21 and A22, then the determinant of matrix A is given by A11 into A22 minus A12 into A21. Determinant of a matrix of order 3 can be obtained by expressing the determinant in terms of second order determinants. You can expand the determinant along each of the 3 rows and each of the 3 columns in terms of second order determinant. Now we will see some properties of determinants. Properties of determinants. First property states that the value of the determinant remains unaltered if its rows and columns are interchanged. Second property of determinants states that if any two rows of a determinant are interchanged, then sign of the determinant changes. Or you can say that value of the determinant gets multiplied by -1. Similarly, this property is true for two columns also. So, you can say that the sign of the determinant changes if any two columns of the determinant are interchanged. Third property. This property states that if each element of a row or a column of a determinant is multiplied by a constant k, then its value gets multiplied by k. This property helps you to conclude that a common factor of all elements of any row or any column can be placed before the determinant. Fourth property. This property states that if any two rows of a determinant are identical, that is, all the corresponding elements of two rows are same, then the value of determinant is 0. Similarly, if any two columns of a determinant are identical, that is, all corresponding elements of two columns are same, then the value of the determinant is 0. Fifth property. The previous two properties helps us to derive that if corresponding elements of two rows are proportional, then the value of the determinant is 0. Similarly, if corresponding elements of two columns are proportional, then the value of the determinant is 0. Sixth property. This property states that if each element of a row of a determinant is expressed as sum of two or more terms, then the determinant can be expressed as sum of two or more determinants. Similarly, if each element of a column of a determinant is expressed as sum of two or more terms, then the determinant can be expressed as sum of two or more determinants. Seventh property. This property states that the value of the determinant remains unchanged if the elements of one row are altered by adding to them any constant multiple of the corresponding elements in any other row. Similarly, the value of determinant remains unchanged if the elements of one column are altered by adding to them any constant multiple of the corresponding elements in any other column.
We can also find area of triangle by using determinants, which is given in a plane and whose coordinates are also given.
We can also find an area of a triangle by using determinants, which is given in a plane and whose coordinates are given. If x1, y1, x2, y2 and x3, y3 are the coordinates of vertices of a triangle, then the area of the triangle is given by 1/2 into determinant containing elements x1, y1 and 1 in the first row, elements x2, y2 and 1 in the second row, and elements x3, y3 and 1 in the third row.
Now we will learn about minors, cofactors, adjoint of a matrix and singular and non-singular matrix.
Minor of an element Aij is denoted by Mij. Minor of an element Aij of a determinant is the determinant obtained by deleting its ith row and jth column in which the element Aij lies. For example, delta is the determinant such that delta is equal to determinant containing elements 1, 2 and 3 in the first row, elements 4, 5 and 6 in the second row, and elements 7, 8 and 9 in the third row. Here, as we can see, 6 lies in second row and third column. It means that 6 is the element A23 in the determinant and its minor M23 is given by M23 is equal to determinant whose first row elements are 1, 2 and second row elements are 7, 8, which is further equal to 8 minus 14, which is equal to minus 6. So here the minor of the element 6, that is M23, is equal to minus 6. Cofactor. The cofactor of an element Aij is denoted by Cij and is defined by Cij is equal to minus 1 raised to the power I plus j into minor of the ijth element, that is Mij. For example, if delta is the determinant whose first row elements are 1, 2 and 3, second row elements are 4, 5 and 6 and third row elements are 7, 8 and 9, then the minor of the element 6, that is M23, is equal to determinant whose first row elements are 1 and 2 and second row elements are 7 and 8, which is equal to 8 minus 14, which is equal to minus 6, and the cofactor of 6 is given by c23 is equal to minus 1 raised to the power 2 plus 3 into M23, which is equal to minus 1 into minus 6, which is equal to 6. Adjoint of a matrix. The adjoint of a square matrix A is the n by n order matrix whose elements are Aij and is defined as the transpose of the matrix Cij of n by n order, where Cij is the cofactor of the element Aij. For example, the cofactors of matrix A whose first row elements are 1, 2 and second row elements are 3, 4 are given as C11 is equal to 4, C12 is equal to minus 3, C21 is equal to minus 2 and C22 is equal to 1. Now C is the matrix of the cofactors whose first row elements are 4, minus 3 and second row elements are minus 2, 1. So the adjoint of matrix A is given by transpose of matrix C, that is equal to matrix whose first row elements are 4, minus 2 and second row elements are -3, 1. Singular and non-singular matrix. A matrix A is said to be singular if determinant of A is equal to 0. Otherwise, it is called non-singular.
Now we will discuss about invertible matrix, inverse of a matrix, and some results on invertible matrices.
Invertible matrix. If A and B are two square matrices such that A into B is equal to B into A is equal to identity matrix I, then B is the inverse matrix of A and is denoted by A inverse, and A is the inverse of B. Matrix B is called inverse of matrix A, and matrix A is called inverse of matrix B. Inverse of matrix A is denoted by A inverse. Thus, A into A inverse is equal to A inverse into A is equal to identity matrix I. Also, we know that product of matrix A and adjoint of matrix A is equal to determinant A into identity matrix I, that is A into adjoint of A is equal to adjoint of A into matrix A, which is equal to determinant of matrix A into identity matrix I of same order as A. This implies that A into adjoint of matrix A upon determinant of matrix A is equal to adjoint of A upon determinant of A into matrix A, which is equal to identity matrix I. Therefore, we can say that A inverse is equal to adjoint of matrix A divided by determinant of A. The necessary and sufficient condition for a square matrix A to possess inverse is that matrix A is singular, that is, the determinant of matrix A cannot be 0. Results on invertible matrices. Now we shall discuss some results on invertible matrices. First result is that an invertible matrix possesses a unique inverse. It means that an invertible matrix can have only one inverse of itself. We can prove this result by using contradiction. Contradictory, we assume that B and C are two inverses of a given matrix A. Let A be an invertible matrix and B as well as C be the inverse of A. Then A into B is equal to B into A, which is equal to identity matrix I, and A into C is equal to C into A, which is equal to identity matrix I. Now, matrix B, which is also written as B into identity matrix I, will be equal to B whole multiplied by A into C, which is equal to B into A whole multiplied by C, which is equal to identity matrix I into C. So, matrix B is equal to identity matrix I into matrix C. We can say that matrix B is equal to matrix C. Therefore, inverse of any matrix is unique. Now the second an important result of invertible matrix is that if A and B are two invertible matrices of the same order, then the inverse of product of matrices A and B is equal to B inverse into A inverse. We can prove this result by the definition of inverse of a matrix, as we know that the product of a number and its inverse is equal to I. So, the product of matrix A into B and their inverse is equal to I. That is, A into B into inverse of A into B is equal to I, which implies that A inverse whole multiplied by A into B whole multiplied by inverse of A into B is equal to A inverse into identity matrix I of the same order as matrix A and B. Pre-multiplying both sides by A inverse, we get A inverse into A whole multiplied by B into inverse of A into B is equal to A inverse, because we know that A inverse into identity matrix I is equal to A inverse. This implies identity matrix I into B into inverse of A into B is equal to A inverse, which implies that B into inverse of A into B is equal to A inverse. Now, pre-multiplying both sides by B inverse, we get B inverse into B into inverse of A into B is equal to B inverse into A inverse. Or we can say that identity matrix I into inverse of A into B is equal to B inverse into A inverse, which implies that inverse of product of matrices A and B is equal to B inverse into A inverse. So, inverse of product of two matrices is equal to the product of their inverses in reverse order. Hence, inverse of A into B is equal to B inverse into A inverse.
ਹੁਣ ਤੱਕ ਤੁਸੀਂ adjoint of matrices, invertible matrices ਅਤੇ inverse of matrices ਬਾਰੇ ਸਿੱਖਿਆ ਹੈ। ਆਓ ਹੁਣ ਇਹਨਾਂ ਤੇ ਆਧਾਰਿਤ ਕੁਝ ਉਦਾਹਰਣਾਂ ਨੂੰ ਹੱਲ ਕਰੀਏ।
Let us see an example. Find the adjoint of a matrix A, which is a 3 by 3 order square matrix whose first two elements are 3, minus 2, 3. Second row elements are 2, 1, minus 1, and third row elements are 4, minus 3, 2. Hence, find the inverse of matrix A. ਭਾਵ ਦਿੱਤੀ ਗਈ 3 by 3 order square matrix A ਜਿਸ ਦੀ ਪਹਿਲੀ ਰੋ ਦੇ ਐਲੀਮੈਂਟਸ 3, minus 2, 3, ਦੂਜੀ ਰੋ ਦੇ ਐਲੀਮੈਂਟਸ 2, 1, minus 1 ਅਤੇ ਤੀਜੀ ਰੋ ਦੇ ਐਲੀਮੈਂਟਸ ਹਨ 4, minus 3, 2. ਇਸ ਮੈਟ੍ਰਿਕਸ A ਦਾ ਐਡਜੁਆਇੰਟ ਪਤਾ ਕਰੋ। ਨਾਲ ਹੀ ਇਸ ਦਿੱਤੀ ਮੈਟ੍ਰਿਕਸ A ਦਾ ਇਨਵਰਸ ਵੀ ਪਤਾ ਕਰੋ। Now we will see its solution. Here we are given matrix A, which is a 3 by 3 order square matrix whose first two elements are 3, minus 2, 3. Second row elements are 2, 1, minus 1, and third row elements are 4, -3, 2. Now, in order to find the adjoint of the given matrix A, first of all, we have to find the cofactors of this matrix A. Now, as we know that cofactors of an element Aij lying in the ith row and jth column, that is Cij is equal to -1 raised to the power I plus j into Mij, where Mij is the minor of the element Aij lying in the ith row and jth column. Therefore, using this formula, cofactors of A are C11, which is equal to -1 raised to the power 1 plus 1 into M11 will be equal to -1 raised to the power 2 into determinant, whose first row elements are 1, -1 and second row elements are -3 and 2. On solving, it will be equal to 2 minus 3, which is equal to -1. Therefore, here C11 is equal to -1. Similarly, C12 will be equal to -1 raised to the power 1 plus 2 into M12, which is equal to -1 raised to the power 3 into determinant, whose first row elements are 2 and -1 and second row elements are 4 and 2. Which on solving is equal to minus of 4 minus -4, which is equal to minus of 4 plus 4, which is equal to -8. Therefore, here C12 is equal to -8. Similarly, C13, which is equal to -1 raised to the power 1 plus 3 into M13 will be equal to -10. So here C13 will be equal to -10. In the similar way, C21, which is equal to -1 raised to the power 2 plus 1 into M21, which is equal to -5. So here C21 will be equal to -5. Now C22, which is equal to -1 raised to the power 2 plus 2 into M22 will be equal to -6. So here C22 will be equal to -6. Similarly, C23, which is equal to -1 raised to the power 2 plus 3 into M23, which is equal to 1. So C23 is equal to 1. C31, which is equal to -1 raised to the power 3 plus 1 into M31, which is equal to minus 1. So here C31 is equal to minus 1. Now C32, which is equal to minus 1 raised to the power 3 plus 2 into M32, which on solving is equal to 9. So here C32 is equal to 9. Lastly, C33, which is equal to minus 1 raised to the power 3 plus 3 into M33, which is equal to 7. So here C33 will be equal to 7. Therefore, here matrix C, that is the 3 by 3 order square matrix of cofactors, will be a matrix whose first two elements are minus 1, minus 8, minus 10. Second row elements are minus 5, minus 6, 1, and third row elements are minus 1, 9 and 7. Therefore, adjoint of A, which is denoted as, is the transpose of this cofactors matrix C. Therefore, adjoint of given matrix A will be equal to transpose of a 3 into 3 order square matrix whose first row elements are minus 1, minus 8, minus 10. Second row elements are minus 5, minus 6, 1, and third row elements are minus 1, 9 and 7. On taking transpose, it will be equal to 3 by 3 order square matrix whose first row elements are minus 1, minus 5, minus 1. Second row elements are minus 8, minus 6, 9, and third row elements are minus 10, 1 and 7. So here adjoint of A is equal to a 3 by 3 order square matrix whose first row elements are minus 1, minus 5, minus 1. Second row elements are minus 8, minus 6, 9, and third row elements are minus 10, 1 and 7. Now further, in order to find the inverse of the given matrix A, first of all, we will have to find the determinant of matrix A. So, here determinant of A will be equal to 3 into determinant whose first row elements are 1 and minus 1, and second row elements are minus 3 and 2, minus of minus 2 into determinant whose first row elements are 2 and minus 1, and second row elements are 4 and 2, plus 3 into determinant whose first row elements are 2 and 1, and second row elements are 4 and minus 3. This is equal to 3 into 2 minus 3 plus 2 into 4 plus 4 plus 3 into minus 6 minus 4. On solving, determinant of A is further equal to 3 into minus 1 plus 2 into 8 plus 3 into minus 10, which is further equal to minus 3 plus 16 minus 30, which is equal to 13 minus 30, which is equal to minus 17. Now, as here determinant of matrix A is equal to minus 17, which is not equal to 0, therefore matrix A is non-singular and so its inverse exists. Now, as we know that inverse of a matrix A, that is A inverse, is equal to adjoint of A upon determinant of A therefore, here A inverse will be equal to minus 1 upon 17 into 3 by 3 order square matrix whose first row elements are minus 1, minus 5, minus 1. Second row elements are minus 8, minus 6, 9, and third row elements are minus 10, 1 and 7. Which is equal to 3 by 3 order square matrix whose first row elements are 1 by 17, 5 by 17, 1 by 17. Second row elements are 8 by 17, 6 by 17 and minus 9 by 17. And third row elements are 10 by 17, minus 1 by 17 and minus 7 by 17. Therefore, here A inverse is a 3 by 3 order square matrix whose first row elements are 1 by 17, 5 by 17 and 1 by 17. Second row elements are 8 by 17, 6 by 17 and minus 9 by 17. And third row elements are 10 by 17, minus 1 by 17 and minus 7 by 17. Which is the required solution. In this episode, you have learnt about adjoint of matrices, invertible matrices and inverse of matrices.
ਇਸ ਐਪੀਸੋਡ ਵਿੱਚ ਤੁਸੀਂ adjoint of matrices, invertible matrices ਅਤੇ inverse of matrices ਬਾਰੇ ਸਿੱਖਿਆ ਹੈ। ਮੈਂ ਉਮੀਦ ਕਰਦੀ ਹਾਂ ਕਿ ਤੁਹਾਨੂੰ ਇਹ ਐਪੀਸੋਡ ਪੂਰੀ ਤਰ੍ਹਾਂ ਸਮਝ ਆ ਗਿਆ ਹੋਵੇਗਾ। ਧੰਨਵਾਦ।